All right, so today we're going to talk about the derivatives of the last set of family of functions that we know, which are logs and exponential functions. All right, so I need you to take out your calculator, if you will, your 89, your wonderful 89. And we're going to find some limits. All right, so we're going to find the limit as x goes to infinity, and use parentheses here, 1 plus 1 over x to the x. And I have a graph already here, but you guys can do the limit, you know, the f3 function limit. And what do you get? That's 0. Besides the bell. You got it? I've got one. It's E. The whole thing is 2, right? The whole thing is 2 the x. All right, did somebody get E? This is E. Now, this is a limit all calculus students should know. And I'm going to just refresh your memory here. What about this equation here? Do we remember what that is? This is compounding interest, right? This is P final, and this is actually P initial, right? The initial amount that you invest. Does that look familiar? Kind of looks like this. I could rewrite this as P initial times 1 plus R over N to the N times, or raised to the T, couldn't I? And what is this? On one of our tests last year, we figured out that this was E to the R. Interesting, right? Because then it becomes P e to the RT, which is PERT, which is compounding continuously. What would happen if you did your limit calculation again and you put a 2 here over the x? 2 over x. What do you think you're going to get? E squared. Pretty cool, huh? All right, so whenever you see a limit that looks like that, it's going to be E. What about this limit? Let's do this one in your calculator. The limit as x approaches 0 of e to the x minus 1 all over x. Are we having trouble doing the limit? Yes. Command? All right, so the limit, I'm wondering what. So we go LIMIT, that comes up, right? And then you're going to put parentheses, E caret x minus 1, close parentheses, divide by x, comma, x. And then what is x approaching? 0. That's how you type it in the calculator. And it equals 1, doesn't it? And then for your benefit here, what did I do? I actually put a sketch of this function, e dx minus 1 over x, here to the right. And you can see that as x gets closer and closer to 0, that y gets closer and closer to 1. Now, ordinarily, when we have a function where we have a denominator, what do we expect here when x is 0? A domain error, yes. But that you can't remove, we would expect a vertical asymptote, wouldn't we? What's going on here? It's removable. This is actually a removable discontinuity sitting right here. instead of a vertical asymptote. And that's because the rate of change of x, what's the slope of x? 1. And believe it or not, the slope of e to the x minus 1 at x equals 0 is 1. So their rates of change are the same. So they approach 1 there. I know, and we're going to learn more about that when we talk about L'Hopital's rule. But I'm not ready to discuss that quite yet, okay? Just know that that's removable and not an asymptote there. This is another limit that all AP Calculus students should know, which means we're going to be on the lookout for it today, okay? All right, moving right along. Now we're going to find the derivative of e to the x. This one's my favorite function, and we're about to find out why. So if I say f of x is equal to e to the x, going back to our limit language, what's f prime of x? It's equal to the limit as h approaches 0 of, remember it's f of x plus h minus f of x all over h. All right, so now we're going to plug in our values here. The limit as h goes to 0 of, now what do the instructions tell us to do here? Plug x plus h in for x, so we're going to get e to the x plus h minus, what's f of x? E to the x all over h. The limit as h goes to 0. Now the properties of exponents will allow us to bust up e to the x plus h. I could rewrite this as e to the x times what? E to the h, because when you have the same base, you are adding the exponents when you are multiplying, minus e to the x all over h. And now do you see something we can do mathematically? Factor out an e to the x, and we get e to the x times, well, what's left? E to the h minus 1 over h. And I wrote it this way for a reason. Do we know what this limit is? Did we just figure out what that limit was? We said that just a moment ago that this one was going to equal 1. E to the x minus 1 over x as x approaches 0 is the same as e to the h minus 1 over h as h approaches 0. And so then we're left with e to the x. So what's the derivative of e to the x? How wonderful is that? E to the x is its own derivative. Yeah, that's really cool. So we can say if y equals e to the x, dy dx is equal to e to the x. That's great. But what happens if I have a function other than e to the x, or to the x up there? I have y equals e to the f of x. What do you think I have to do now? I have to use the chain rule, right? Because what is the outside function here? It's e to the x. The inside function is f of x because I composed it by plugging in f of x where x is. And so then dy dx here is going to be, what's the derivative of the outside function? Keeping the argument, e to the f of x times the derivative of the inside, which is f prime of x. You just take it and you multiply it by the derivative of the exponent. Really easy derivative to take. Really easy derivative to take. We got it? Well, naturally, we have to take the derivative of its inverse, which is the natural log of x. So f of x is equal to natural log of x. Now, I don't want to use limits here with the natural log of x. So I'm going to write y equals the natural log of x. And I'm going to exponentiate both sides. Now, what do I mean by that? We're going to raise both sides to the e, because I can take the derivative of e to the function now. And we have e to the y equals, what happens when I raise e to the ln of anything? These two are going to, in effect, cancel, and we're just going to get an x here. And now we can take the derivative how? Yeah, that's right. Taking the derivative implicitly. So what's the derivative of e to the y? E to the y times the derivative of the inside, which is dy dx equals, well, what's the derivative of x? 1. And so then dy dx is equal to 1 over e to the y. That's great, but I'd like to have it in terms of x. But what do we know? But e to the y is equal to x. So this is the same thing as saying dy dx is equal to 1 over x. So the derivative of the natural log of x is equal to 1 over x. Now, let's have a discussion here about the natural log graph. We know that it has a vertical asymptote at x equals 0, and then it looks like this. And what is its domain? That's right, 0 to infinity with parentheses. Now I'm going to graph its derivative. What's its derivative? It's 1 over x, isn't it? We remember what it looks like. For the record, their finger motions are doing this in the air. Right? Only I could see it. And so this is 1 over x. Now this is the derivative, right? This derivative here is supposed to give you all the values of the slopes to natural log of x. But now I'm going to ask you, what's going on with the domain of the derivative? If you look at it. It's negative infinity to 0 and union with 0 to infinity, but is that what's going on up here? Can I have slopes to ln of x if ln of x doesn't exist over here? So this does not apply, and so we have to say for x greater than 0, does that apply? Does that make sense to everybody? All right, big deal there. All right, so let's do a little summary chart. We say y equals natural log of x. We said dy dx was 1 over x. But what happens if you have y equals the natural log of some function other than just x? What's the outside function here? Natural log of x. The inside is f of x, so it's a composite. And so the derivative of a composite using the chain rule is going to be, what's the derivative of the outside function? 1 over x, keeping the argument, so it's 1 over f of x times the derivative of the inside, which is f prime of x. Now, a lot of people make it very easy on themselves and go, well, that's just the derivative over the function itself on the inside. So it's f prime of x over f of x, because this is really over 1 here. All right? So the derivative of e to the x, very easy. The derivative of ln of x, very easy. 1 over x, or 1 over the function times the derivative of the inside. But what if it's not e? And it's some other base, like 2 or 3 or 5 to the x. All right, here we go. We're going to say y equals a to the x. How am I going to get that x down? We're going to take the The log of both sides. And we're going to take the natural log of both sides because I know how to take the derivative now of the natural log. So this is going to be natural log of all of this. So on the left side, I'm going to get the natural log of y equals, good, x, natural log of a. And now we're going to take the derivative how? That's right. Okay, what's the derivative of the natural log? We said it was 1 over. So this is going to be 1 over y dy dx, right? Because that's the derivative of the inside. Equals, now, natural log of a. A is just a number, so it's going to be like the natural log of 2. Natural log of 2 for you chemistry people is 0.693, right? Roughly? Is that just a number? The answer is yes. So ln of a, looks like I would do that. Ln of a, the natural log of a, is a constant. So what is a constant times x's derivative?
The constant.
The constant. So this would be just the natural log of a. Because the derivative of x is 1. And then so we can say that this is dy dx times natural log of a times y, because we're solving for dy dx. I'm multiplying both sides by y. Do you agree with that? But what is y? It's equals, you're right. That's why you were looking at me crazy. I was being crazy. But what does y equal? A to the x. Yes. So that's going to be natural log of a times a to the x is dy dx. So if you have a base other than e, the derivative is going to be the natural log of the base times a to the x. Let's pretend our base was e. It would be the natural log of e, which is 1 times e to the x. So, you know, you could even use this for e, but e is so much nicer. All right, so let's do our little summary. If we have y equals a to the x, dy dx is going to equal the natural log of a times the function itself again. And then what if I have y equals a to the sum f of x here? The composite, right, with f of x being the inside. So dy dx will be natural log of a times a to the f of x times the derivative of the inside, which is f prime of x. Yes, so you always take the derivative of the exponent. Questions on that? What if we were taking the derivative of log base a of x? Pardon me? You could, and then it would be a to the y, right? But what I would do here is change the base. Do we know how to change the base?
The base formula.
All right, so if I have log base a of x, what does that equal in terms of natural log? I'm going to have natural log on top and natural log on the bottom, right? So the base goes in the basement. So the base here is what, a? And then the argument for the a goes in the attic here. Do you remember us doing that? Okay, so then I'm going to rewrite this saying y equals the natural log of x over the natural log of a. Now, what is the natural log of a? We just have a it's a constant. So it's just going to go along for the ride here. So I'm going to even rewrite this as y equals 1 over the natural log of a, which is just a number, times the natural log of x. So if I take the derivative, it would be dy dx equals the constant, which is 1 over the natural log of a, times the derivative of ln x, which we said was 1 over x. So this is going to be 1 over the natural log of a times x. So let's do our summary chart. So if y equals log base a of x, dy dx will equal 1 over the natural log of a times x. What happens if it's y equals a log base a of f of x? Dy dx will be what's the only thing different? Instead of x on the bottom, it will be, so it would be 1 over the natural log of a times f of x times the derivative of the inside, which is f prime of x. And most people will write this as f prime of x over the natural log of a times f of x. Now, these are rules, right? They're rules. I would not derive every time I take a derivative of a log or exponential. I wouldn't derive it every time. I would just apply the rule. Okay? I'm not asking you to derive them every time. Yes, ma'am.
When you say 1 over ln a times times 1 over x, isn't it 1 over ln a just go to 0?
I'm not taking the derivative of ln a.
But it says you have y equals ln x over ln a. It's fine.
Yeah.
Like that, and then you take the derivative.
Right. I could use the product rule here, but 1 over ln a is a constant. So I'd write first d second, which would be this, plus second, which is ln x times the derivative of a constant, which is 0. Yeah, it goes away. Okay, good question. All right. Moving along, I have some examples from the homework. Now, you guys have to do from the book, if I recall. 1 through 41 odd. Now, you might be saying to yourself, 1 through 41 odd sounds like a large number of problems. Okay, so I'm going to do some of the evens to make you feel better, shall we? Okay, so number 2. Y equals e to the 2x. And you're going to see how fast this homework's going to go. I'm finding the derivative. dy dx is equal to e to the 2x times the derivative of the exponent, which is 2. So I would write this as dy dx is equal to, and I always put the 2 in front, 2e to the 2x. How difficult was that? Not too bad. Number 4. Y equals e to the negative 5x. dy dx e to the negative 5x times negative 5. So that's going to be dy dx equals Negative 5e to the negative 5x. Good. How fast is this going? Pretty fast? I'm trying to sell it to you here. Number 6. Y equals e to the negative x over 4. dy dx is equal to, now, negative x over 4 is equivalent to what, if you wrote it out? Negative 1/4 x, right? So don't let it trick you. Don't use the quotient rule there. Okay, so it's going to be e to the negative x over 4 times negative 1/4. So you can rewrite this as dy dx equals negative 1/4 e to the negative x over 4. Are we sold yet? Number 8. Y equals x squared e to the x minus x e to the x. Now we've amped it up a bit here. What's going on here? We have to use the product rule how many times? Twice. Now there's an easier way to go on this. If you factor out e to the x, you only have to use the product rule once. So let's see what happens when we factor out e to the x. What do we get? We get e to the x times x squared minus x. And now you only have to use the product rule once. God bless you. So let's do dy dx. So it's going to be first, which is e to the x. D second, which is 2x minus 1. Good. Plus second, which is x squared minus x times the derivative of the first. E to the x is our favorite function, isn't it? Now, I can simplify this by factoring out. Do you notice that we have an e to the x here and an e to the x here in that term? May we factor that out? Why, yes, Mrs. Muller. Okay, e to the x. My silent group here. What's left? I have 2x minus 1, and then I have x squared, and then what's 2x minus x? Plus x minus 1. I simplified all at once. Can we do that? Without any... Now, would you get the same answer if you use two product rules? The answer is yes, but it'd be a little bit more difficult. We solved yet? 10. Y equals e to the x squared. Anybody willing to go do this with me? Going to be e to the x squared times 2x. Yes. You're like, Mrs. Muller, there's something going on here. It's going to get more difficult, isn't it? The answer is no, because it's e to the x. So nice. $12. Y equals 9 to the negative x. And do we remember what that rule is? It's okay to say no. You can flip back a couple pages. If y equals a to the f of x, dy dx is ln of a times a to the f of x times f prime of x. So what is dy dx here? Natural log of 9. Good. Times 9 to the negative x times negative 1. So I usually write negative 9, natural log of 9 times 9 to the negative x. So the only difference if you have a base that's different than e is that you have to add the natural log of the base as a multiplier here in that formula. We're on number 14. This is my favorite one. Because everybody in the room goes, why on earth, Mrs. Muller, would anybody raise 3 to the cotangent x? And the reason is just to get you to remember what the derivative of cotangent x is. No? You guys are a tough sell here today. All right, dy dx equals natural log of, right? Natural log of 3 times 3 to the cotangent x times negative cosecant squared x, yes. And I think I would just leave it like that. That's as pretty as it might get there. Number 16 is natural log of x quantity squared. What do we have to use here? We have to use the power combined with the chain. So what's dy dx here going to be? Power down. Function. ln x, lower the power 1 to the first times the derivative of the inside, which is the derivative of natural log. It's 1 over x. Yes. So this is just 2 natural log of x all over x. I don't have any room. I'm going to insert blank page. We're on 18, is that right? We have plenty of examples here. Number 18, y equals natural log of 10 over x. Anybody got any ideas here? We can use a quotient rule on the inside there, but I don't necessarily want to do that. Logs in calculus can be your absolute best friend. What? No, I wouldn't exponentiate. What is the log of a quotient? Ln of the top minus c ln of the bottom. So I'd rewrite this first as this is a natural log of 10, which is just a constant, minus the natural log of x. And now I would take the derivative. dy dx, the derivative of the natural log of 10 is 0, and the derivative of natural log of x is 1 over x. So it's negative 1 over x. So that looked a lot scarier than it was. Number 20. Y equals x natural log of x minus x. Anything you want to do first? Factor out, because we factor out of what? And x. I like that. All right, now what? dy dx is, I'm going to use the product rule, which would be first, times the derivative of the second. What's the derivative of ln x? It's 1 over x, and then the derivative of 1 is 0, plus second, which is natural log of x, minus 1, times the derivative of the first, which is 1, which gives us 1 plus natural log of, natural log of x minus 1, which is just natural log of x. Could we rewrite this to make our lives easier? What does this equal? Log base 5 of x to the 1/2. But then what happens? Well, can I bring the 1/2 in front even? Yes?
Yeah.
So 1/2 log base 5 of x. And Lauren, yes, now I would do what you're suggesting. She's going to change the base to what? 1 over 1/2 times?
ln of x over ln of 5.
Yes. And then what's the derivative of 1 over 2 ln of natural log of 5? That's just, this is a constant, isn't it? So dy dx here is going to be the constant times the derivative of 1 over, ln x, which is just 1 over x. $24. I would change the base here. Can we change the base right here? That's going to be 1 over natural log of x over natural log of 2. And if you rewrite that, that's going to be 1 over, well, I keep the numerator, change the operation, and flip the denominator. There we go. And natural log of 2 is just a constant. So this is equal to the natural log of 2 times ln x to the -1. dy dx is equal to negative natural log of 2 times ln x to the -2 times the derivative of the inside, which is 1 over x. So this is going to be negative natural log of 2 over x times the natural log of x quantity squared. All right. Now I'm foreshadowing a little bit of a lesson next time, but I figure that's a good thing to do because it'll be on virtual day, yes? Take the derivative of what? Well, there's some things in life you don't want to take the derivative of. And I'm going to give you a prime example by looking at this packet. This is going to be what you're going to do on virtual day, okay? This packet I'm handing out right now. And the title of it is take the derivative of what? No way. You know what? The staples, just hang on to that. You hang on to that because the staple's not right. There's 2 of them there, I think. The last staple's not right. The last staple's not right, I'm sorry. Printer must have liked me when they did this. Got it? So you look at the front of this packet and you say, take the derivative of that. Do you want to take the derivative of what you see? The square root of all of that stuff? Because that would be power down function lower power 1 times the derivative of the inside, which is a quotient rule from hell, right? Because a quotient rule from hell has a product on top and a product on the bottom that you have no chance of expanding, right? But guess what? Logs can be our best friends because we can unbundle this. And I'm going to tell you guys about this process called logarithmic differentiation, which is a big fancy word for. I'm going to take the log first and then take the derivative. Okay, so let's take the log of both sides, which would be the natural log of y equals the natural log of 2x plus 1 to the 5th times x to the 4th minus 3 raised to the 6th. Now back in pre-cal, in Algebra 2 Honors, we could unbundle the right side. We could expand the right side using the properties of logs. When you have a log of a product, what can you do? It's plus, right? Because when you multiply, you add the exponents, and logs are nothing more than exponents. And then what could you do with the 5? So we could expand this and say this is the natural log of y equals 5 times the natural log of 2x plus 1 plus the natural, or 6 times the natural log of x to the 4th minus 3. Everybody agree we can unbundle the right like that? And now, could we take the derivative implicitly? The answer is yes. What's the derivative of the left side? It would be 1 over y dy dx, because the derivative of natural log is 1 over the function times the derivative of the inside, equals 5 times, well, what's the derivative of a log of an f of x? It's f prime over, if you have y equals ln of f of x, dy dx is equal to f prime over f of x. So what's the derivative for your inside here? 2. So this is 2 over 2x plus 1. Good. Plus 6 times 4x cubed over. That's right. But what am I solving for? Dy dx. And so I have to take the right side and I have to multiply everything by what? Y. So what's 5 times 2 up here? It's 10 over 2x plus 1 plus 24x cubed over x to the 4th minus 3, all times y. Now, if I gave you a point, could you find the slope? Okay, now if I were to ask you what the function was, or the derivative was as a function of x, what could I replace y with? Yes, the very first part of this, I could replace it with this. So 2x plus 1 to the 5th. So I could rewrite this as 10 over 2x plus 1 plus 24 x to the 3rd over x to the 4th minus 3 times 2x plus 1 to the 5th times x to the 4th minus 3 to the 6th. And that would be the derivative as a function of x. And if you had a value for x, you could give me the slope. Now, does that look like it's a lot easier than using the product rule on the thing that we just saw? Yes? All right. What about this one? I'm multiplying 3 things together. So we're going to take the natural log of both sides. The natural log of y equals. Can you unbundle it with me? What would it be? Root of x, but that's x to the 1/2. So it would be 1/2 natural log of x. You follow that? Plus x squared natural log of e. It will, right. Then plus 10 times the natural log of x squared plus 1. And now we're going to take the derivative. How? Right. Okay, so when we do that, we get on the left side 1 over y dy dx, good, equals 1/2 times, what's the derivative of natural log? 1 over x, so this is 1/2 times 1 over x, plus natural log of e is just 1, so this goes to 1. And the derivative of x squared is just 2x. Plus, and it's going to be 10 times the derivative of the inside, which is 2x over x squared plus 1. And then I need to solve for dy dx, so I'm going to multiply everything by y. So this is dy dx equals 1 over 2x plus 2x plus 20x over x squared plus 1, all times y. Now, Mrs. Muller is not going to make you find a common denominator or anything on the inside there. So are we happy about that? Okay, but what is what? The top. So we can say dy dx is equal to 1 over 2x plus 2x plus 20x over x squared plus 1 times root x e to the x squared times x squared plus 1 to the 10. So how many in here are like in logarithmic differentiation? It's pretty easy, isn't it? What are we going to do with this one? First things first is I'm going to rewrite this as sine of x to the second, and then this will be tan of x to the sixth, all over x squared plus 1 to the second, I'm sorry. Can we unbundle it on the right? Oh, it's to the fourth, you're right. All right, so taking the natural log of both sides, natural log of y equals. Now this has something in the basement, so what's that going to be? It's negative, isn't it? Because it's a quotient. So this would be 2 times the natural log of sine x plus 4 times the natural log of tan x minus, why am I using minus? Because it's in the denominator. Anything in the denominator is minus because it'll be a negative exponent. So this is 2 times natural log of x squared plus 1. And now, may I take the derivative implicitly? Here's my abbreviation. Take the derivative implicitly. 1 over y dy dx equals 2 times f prime over f. What's the derivative of sine? Cosine x over sine x plus 4 times the derivative of tangent, which is now it's secant squared x over tan x minus 2 times, what's the derivative of the inside? 2x over x squared plus 1. And then I'm going to take everything and multiply it by y, because we're solving for dy dx. Dy dx equals 2, and this is cotangent x, by the way, plus 4 secant squared x over tan x, and I wouldn't simplify that, I'd just leave it, minus 4x over x squared plus 1 times y. Could you plug in what y is at the end? The answer is yes. Okay, so that's all I have. And I foreshadowed what your